Welcome back to The Explainer. Today, we're diving straight into the invisible world of radiographic testing for shipbuilding. We spend so much time looking at the massive, imposing exterior of a steel hull, but right now, we're going to look right through it. We'll explore exactly how shipbuilders harness the physics of radiation to guarantee a vessel's structural integrity long before it ever touches the water.
Let's start with a really dangerous illusion. A ship's weld can look completely flawless on the surface, smooth, perfectly aligned to the naked eye, but it could be hiding a fatal cavity deep inside. That invisible cavity creates a massive weak point, and under the relentless, crushing pressure of the ocean, it will eventually fail. It'll snap.
Section 1, the hidden danger, looking past the illusion of perfection.
So, to guarantee the integrity of a massive ship, we have to find those microscopic defects lurking inside the steel. And this is exactly where radiographic testing, or RT, comes in. It's a critical non-destructive testing method that lets us literally see inside solid steel to diagnose its internal health. Obviously, you can't just cut a perfectly good hull apart to check if a weld is sound, right? RT solves this by passing ionizing radiation right through the solid weld, casting an image of the interior onto a detector or a piece of film on the exact opposite side.
So, how does this actually work in practice? Well, the physics are pretty brilliant in their simplicity. You place your radiation source on one side of the weld and your film on the other. As the radiation passes through, the steel absorbs it based on its thickness and density. Dense, thick metal absorbs a ton of radiation, so it appears lighter on the final film. But if there's a void inside that weld, like a trapped pocket of gas or some porosity, that empty space absorbs way less radiation. Because of that, more radiation punches straight through to hit the film, revealing itself as a distinct, darker spot on the radiograph. It's essentially like getting an X-ray at the doctor's office, but for solid steel.
Moving on to Section 2, X-ray versus gamma ray, choosing the right tool for the job.
Now that we've got the physics of radiation absorption down, let's look at how shipbuilders actually generate these rays, because the contrast between our two primary options is super interesting. On one hand, we've got X-ray machines. These generate radiation electrically. They're bulky, they need a constant power supply, but they produce incredibly high-resolution images, making them absolutely ideal for a controlled workshop environment. On the other hand, we have gamma-ray sources. These rely on naturally decaying radioactive isotopes, typically iridium-92 for medium-thickness steel or cobalt-60 for the really thick sections. Because they don't need any electricity and are housed in these compact, heavily shielded containers, these battery-free sources are perfect for dropping into those tight, confined spaces deep inside a ship's structure.
Section 3, what radiography misses, the limits of seeing through steel. As powerful as this technology is, it's not perfect. It seems like magic, right? We're literally peering through inches of dense, hardened steel. But we really have to ask ourselves, if X-rays can see right through solid steel, what could they possibly miss? What hidden dangers might still be slipping past our detectors?
Well, here's the catch. Radiographic testing is fantastic at finding volumetric defects. We're talking about three-dimensional, round voids like porosity, trapped slag, or incomplete fusion. Because they have actual volume, they create a very clear difference in density for the radiation to catch. But it struggles immensely to detect planar cracks. These are essentially tight, two-dimensional fissures in the metal with almost no thickness change. Its detection capability there is remarkably poor, which is exactly why RT and ultrasonic testing are so often used together in the field.
To really picture why it misses these cracks, imagine looking directly at the very edge of a sheet of paper. It practically disappears, right? That is exactly what happens with a tight planar crack running parallel to the radiation beam. Because the crack has almost zero thickness from that angle, there's practically no density change for the film to register. The crack absorbs the same amount of radiation as the surrounding solid steel, so it won't cast a dark shadow on the film. It remains a terrifyingly invisible threat. And that's a huge deal, because planar cracks are exactly the type of flaw that can rapidly spread and literally tear a ship apart under stress.
Which brings us to Section 4, the radiation exclusion zone, the human cost of ensuring safety. We have to ground this incredible non-destructive testing method in the real-world stakes of shipyard safety. The deep irony here is that the very tool we use to ensure the safety of the ship is, by its nature, a massive health hazard. Whether you're using a bulky X-ray tube or a highly radioactive piece of cobalt-60, you're dealing with dangerous ionizing radiation. Because of this, the radiographers must be strictly qualified and licensed. But the biggest impact is honestly on the shipyard itself. Before you can even do an exposure, entire inspection bays must be completely cleared of workers. Warning signs go up, massive safety exclusion zones are set up, and surrounding construction just comes to a grinding halt. Plus, radiation levels on the personnel are strictly monitored using dosimeter badges. Honestly, these massive logistical and safety headaches are a huge reason why ultrasonic testing is increasingly preferred over RT, because it requires absolutely no exclusion zone.
So if radiography requires massive safety exclusion zones, completely disrupts the shipyard, and still manages to miss incredibly dangerous planar cracks, how do we confidently find the defects that X-rays leave behind? For our next explainer, we'll dive into how shipbuilders use high-frequency sound waves to echo inside the steel and catch the exact cracks that are completely invisible to radiation.